If you serve a model using the standard vllm package, installing it builds a 9.1 gigabyte virtual environment. But installing a custom C++ port, vllm.cpp, yields a single binary. It takes up just 66 megabytes. To test if that massive compression actually works, we have to look at a high-end setup, an NVIDIA GB110 GPU serving the Qwen 36 27 billion parameter model. You would expect a 141-to-1 reduction in file size to cripple performance. It doesn't. The two engines operate at exact throughput parity. The tiny C++ port actually tracks slightly ahead in a single stream, pushing 86 tokens per second against the Python SAX 82. That specific port is part of a larger project. The team at LocalAI rewrote 18 of their inference backends entirely from scratch in C and C++, intentionally choosing to build the core architecture themselves rather than wrapping upstream code. What they published alongside those ports is rare. It is the first set of public measurements separating the physical footprint of a LocalAI stack from its actual raw speed capabilities. It is tempting to look at a 66 megabyte engine and assume this was a crusade for speed. We intuitively expect that stripping away Python automatically forces everything to run faster. That isn't how the industry usually operates. The standard approach for integrating a new model is simply to wrap the original reference engine. It usually costs a developer nothing more than a Docker file and a gRPC shim to get things working. But a CUDA-only Python stack carries massive friction. It inherently fails to run on half the machines a typical user base actually owns, and it forces the target machine to resolve incredibly complex dependency trees at install time. LocalAI's decision to hand-write its engines is a calculated trade. They exchange massive maintenance hours for the ability to deploy on hardware where a Python stack would fail. This table charts throughput scaling of the Python stack against the C++ port up to 32 concurrent streams. In the single stream column, the port leads slightly, but scaled up, the gap vanishes. Factoring in the 0.5% noise band, the difference is statistically insignificant. The slight slowness that remains has nothing to do with Python. It's simply that ggml's generic CUDA convolution kernels trail slightly behind NVIDIA's highly tuned cuDNN libraries. Only the single stream case sits clearly outside the noise. For heavy, batched workloads, writing a bare metal C++ port on a GPU yields a tie at best. For years, there has been a persistent belief among builders that Python overhead is the primary reason local model serving feels slow. This dataset dismantles that assumption. We covered this recently when discussing MLX VLM running on Apple Silicon. The marketing materials heavily emphasized that removing translation layers and wrappers was a core performance feature. We now have the empirical data to test that exact marketing thesis. When you drop the Python wrapper on a GPU and actually run the numbers, you don't get a speed multiplier. You get a statistical tie, forcing you to look elsewhere for the real bottleneck. So if the speeds match, how do we know this tiny binary isn't quietly cutting corners or degrading the output to keep up with the larger engine? The team instituted a strict parity methodology. First, they consolidate the model weights and tokenizer into a single gguf file. Second, they enforce mathematical verification against the Python original. The build stops until a 100% match is achieved. Only then does optimization begin. The result is that the C++ output is token for token identical to vllm at every single point on the concurrency curve. For researchers, this creates a perfectly controlled substitution. If you swap the runtime engine and observe a behavioral change in the output, you know definitively that the variance belongs to the model itself, not the serving stack. LocalAI published data for 3 other custom ports, and the results vary widely. 1 clear speed win on CPU, 1 memory draw, and 1 outright loss against the standard ONNX runtime. The clear win was a depth estimation model called depth anything. On a CPU, the C++ build runs 1.31 times faster than the PyTorch original, while consuming less than a third of the host RAM. But the most crucial metric for scale is the cold start. Load times plummeted from 749 milliseconds down to just 40 milliseconds. This highlights the real nightmare of deploying a Python stack in production, trying to resolve massive dependency trees against random glib and CUDA versions at 2 in the morning. If you want the real architectural numbers the day they land, subscribe. On scalable infrastructure, getting an 18 times reduction in load time and guaranteed deterministic installation is worth vastly more than a few extra tokens in inference. There is an operative caveat to all of this. The headline compression ratio and the actual hardware ratio required to run these models are two completely different numbers. We see a massive 141-to-1 reduction in disk space, shrinking 9.1 gigabytes down to a 66 megabyte binary. But looking at the actual host memory required to run the model, the cost only drops from 28.18 gigabytes to 24.88. That 141-to-1 storage savings on your hard drive does not buy you any extra GPU memory headroom. You still need the exact same NVIDIA GB100 hardware to serve this 27 billion parameter model either way. Your operational hardware budget does not change. That brings us to the singular, massive cost omitted from all of these benchmark tables: continuous maintenance liability. LocalAI built 18 of these ports from scratch. They now own 18 distinct engine code bases, requiring constant manual updating. The open weights ecosystem moves incredibly fast. When an upstream project changes its architecture, these custom engines must be reported, or they immediately stall out. The engineering report provides exactly 0 data on the headcount or the man-hours required to execute those reports. The 66 megabyte binary is a triumph of footprint, but its real-world success rests on the team's ability to stay relevant as the open weights zoo evolves over the next 6 months.